It is IR spectroscopy and mass spectroscopy both, or just the spectroscopic identification?
I think both.
Okay, then we'll go with both the videos once.
Yeah, sure.
One, two, breathe. 3, 4, and
Lesson 21.1 is mainly just looking at the proton nuclear magnetic resonance spectrometry in a lot more detail. So please go back to the standard level demo that I made of the different ways that the protons will spin and how that creates a magnetic field. Before I get into the spin coupling, let's go into detail on TMS, tetramethylsilane standard, and you need to know why we use it. We use it because it doesn't interfere with the compounds we're trying to deal with. It does that because silicon behaves differently than the carbon. So it has a lower electronegativity, so the line will not overlap with carbon. It's also got the advantage in that it's chemically inert, it's soluble in organic solvents, and you can boil it off easily, and all the hydrogens are in the same environment. So it makes a very simple, easy one to recognize. It won't interfere and it can be separated. Just a few other notes too to help you with the problem solving. Protons on the same atom do not split, they all spin in the same direction. Protons on non-adjacent atoms do not interact with each other, they're too far away, and the proton on the hydroxyl group generally doesn't split. So here we have an example of a proton that's spinning in one direction. It's spinning in this direction here, and so what you have is, if this proton's here spinning in the same direction, it's going to increase the magnetic effect that it has. If it's spinning in the opposite direction, it's not going to cause as great an effect, because it's going to shield out the magnetic effect. And please go to the standard level to have a look at that. So we're going to have a look here at an example with ethanol, and we're going to look at the effect of this either spinning up or spinning down, assuming that all these hydrogens in this environment are spinning up. So when it's spinning up and this one is also spinning up, that's called shielding. And shielding is going to allow a greater energy release, and that's called a movement downfield. And so what we have here is a greater amount of energy, magnetic field energy being created. Now with this particular one here, downward, that one's called deshielding, and so it's going to decrease the amount of energy that proton's going to have, the magnetic force. And so in high resolution we're going to be able to see that we're not just going to see one peak, we're going to see two. Alright, so because there is one neighboring hydrogen, it's going to cause a two split. Now if we look at this hydrogen here and the effects of the spins on these three here, we're going to get a range of things happening here. So if all the protons are aligned, it's going to increase the magnetic field. All of them against, it's going to decrease it, and then we can get all sorts of other combinations. So we can end up sort of having two up in different combinations or two down in different combinations, and if you add that up, it comes to this sort of peak here. So you've got like a 3-layer here, a 3-layer high here, and this is just 1 layer here, and so that's the different shape, and it's got 4 peaks, and so you can see again it's 3 neighboring plus 1 equals the number of peaks, or the number of peaks is 4 and minus 1 gives you 3, gives you the number of neighboring hydrogens. And here's another example here, and splitting doesn't occur with hydrogens in the same environment, which is this here. And so you're going to get combinations here. You'll get a 3-peak one here, and this one here you'll get a 2-peak. And this here is just in written form, just to tell you how the deshielding occurs, but this time we're looking at parts per million. And so if you have got shielding here, it's going to decrease it, so there's a lower chemical shift, so it's going to be higher up on the parts per million graph this time, not an energy graph of tetramethylsilane. And if it's a lot stronger, it'll be a much stronger parts per million downward shift from the standard, which is over here. So here we have it. HA only has 2 small peaks on high resolution, and this is low resolution here, this is low resolution here, and this one here is influenced by 2 more, 2 neighboring, so that's got 3 peaks. So here are the rules, just what I've said before. Number of splits on a peak are counted, and that tells you the number of hydrogens, so just n plus 1. What I haven't told you is how to work out the number of peaks. So to work out the number of peaks, use Pascal's triangle. So put a 1 here, and then you add up the neighboring things. So 0 plus 1 is 1, 1 plus 1 is 2, 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 2 is 3, 3 plus 1 is 4, and so forth. And so by looking at these things here, you can work out the number of peaks. If you know the number of neighboring hydrogens, you know the number of peaks, and if you know the number of peaks, you can also work out the pattern of those peaks. Now what you won't have to do is an integration of the area under the graph, but the integration of the area under the graph also gives you the actual relative number of hydrogens. So here we have a problem. The feature of some proton nuclear magnetic resonance spectra is the electron absorbing withdrawing effect of electronegative atoms. These atoms cause nearby protons to produce peaks at higher chemical shift values, often in the range of 2.5 to 4.5 parts per million. Consider the spectrum of compound D, C4H8O2, and you've just told that it does have a COO bond. The integration here tells us how many hydrogens there are for each of those peaks. By using Pascal's triangle here, we can also match up the patterns with the peaks to also confirm the number of hydrogens. So the peaks equal the number of hydrogens plus 1, so the number of hydrogens equals basically the peaks minus 1. Looking down at the values then, 3.3, 2.3 and 1.1, we can then go to the data booklet and look up the possibilities there. For the 1, that's quite easy, it must be a CH3. The next one here, we've got 2 possible compounds. We know there's a C double bond O. Lastly, for this one, 3.3, that only fits in there with an alcohol. So we can grab those 3 things and match them up together. So the only solution for that is methyl ethanoate C4H8O2. We can then do a double check. Yes, it does have a C double bond O. We can double check the number of neighboring hydrogens. That also checks out. And so all the pieces of the puzzle.
Is it clear till here? Any doubts, Roshan?
No, ma'am.
Depending on the peak, right? You can
Yeah.
do it. You want to
Excellent.
try it? Should I remove all the answers and then you can give a try once again?
Sure. I can try.
Just give me 1 minute. I'll just...
COO bond. The
Yeah.
Yeah, ma'am, I'll open the data booklet now.
Yeah. You want me to open it or you'll open it? You have it with you.
Yeah, I'll open it.
Okay.
Just give me 2 minutes. Ma'am, can I go a bit back?
You want me to go a bit back?
Yeah, I think there's another line below the graph. Yeah, that's enough.
and you've just told that it does have a
Once you're done, let me know, okay?
Yeah, ma'am, 1 minute. Okay, got it, ma'am.
Got it? Check it then. I'm just
Yeah.
presenting.
COO bond. The integration here tells us how many hydrogens there are for each of those peaks. By using Pascal's triangle here, we can also match up the patterns with the peaks to also confirm the number of hydrogens. So the peaks equal the number of hydrogens plus 1, so the number of hydrogens equals basically the peaks minus 1. Looking down at the values then, 3.3, 2.3, 1.1, we can then go to the data booklet and look up the possibilities there. For the one, that's quite easy, it must be a CH3. The next one here, we've got two possible compounds. We know there's a C double bond O. Lastly, for this one, 3.3, that only fits in there with an alcohol. So we can grab those three things and match them up together. So the only solution for that is methyl ethanoate C4H8O2. We can then do a double check. Yes, it does have a C double bond O. We can double check the number of neighboring hydrogens. That also checks out. And so all the pieces of the puzzle match, and that seems to be the only solution that we can come to. X-ray crystallography, they've just...
Did you check it? This is the final one.
Yeah, ma'am, I checked it.
Got it all?
Yeah. I forgot to check it with the C4H8O2, but it seems correct on me.
You want me to go back still bit?
No. You can go ahead. I got it.
Okay.
and so all the pieces of the puzzle match, and that seems to be the only solution that we can come to. X-ray crystallography, they haven't asked you to do the different diagrams, the Bragg's law, and how to draw it and how to do the calculations. I think they leave that to the physics guys. And so you just need to know that this is using X-rays, and the way that X-rays this time interact with the different bond lengths and angles and create a various pattern, and then we use mathematics to determine large complex 3D structures such as DNA and various RNA and protein molecules.
Okay, we'll go with IR and mass spectroscopy.
Yeah.
IR spectroscopy first.
Grammarly can help you write quickly and confidently, so you never have to slow down at work. Instant correction.
In this video, we're going to focus on IR spectroscopy, specifically how to use it to identify functional groups in organic molecules. So let's compare the carboxylic acid with an alcohol. When you have a carboxylic acid, you're going to have a very strong, very broad OH stretch. This OH stretch, it shows up at a signal between 2500 and 3300 centimeters to the -1, which is a type of wave number. Now, the carboxylic acid also has a very strong CO stretch. And the CO stretch, it shows up at a signal of 1700 wave numbers. Now, you may want to write these numbers down because you'll need it in order to identify these functional groups in IR spectrums. Now, the alcohol, it only has the OH group. So it has a strong absorption around 3200 to 3600. So that's the OH stretch of the alcohol group. Now let's move on to our next two molecules, the aldehyde and the ketone functional groups. Both molecules contain the carbonyl functional group, and the CO stretch of these two functional groups is very similar to...
Lata, Jone. Roshan, just give me 1 minute, okay?
Yeah, sure, ma'am.
to a carboxylic acid. It's around 1700. Now, the distinguishing feature between an aldehyde and a ketone is the CH stretch of the aldehyde. This signal here is the alkane CH stretch.
Sorry, Roshan, I took long. This thing came. My
Which
iron
typically
per
shows up for almost all organic molecules that has a CH functional group, and that's around 2900. So you'll see that for the ketone as well. But this part here, this identifies the aldehyde over the ketone. So the aldehyde will have a signal of around 2700 centimeters to the minus 1. So that is the aldehyde CH stretch. So that corresponds to that part of the aldehyde functional group. So that's how you can distinguish an aldehyde from a ketone. It's the presence of this signal, the aldehyde CH stretch. Now let's compare the ester and the ether. The ester functional group has a carbonyl CO stretch of around 1700. Very similar to aldehydes and ketones. The ether it doesn't have the carbonyl CO stretch, but it does have a single bond CO stretch, and that is between 1000 and 1150. So something that you want to take into mind is that double bonds have higher wave numbers than single bonds. The C double bond O stretch absorbs at a higher energy than the CO stretch of an ether. And triple bonds have even higher wave numbers than double bonds. We'll talk more about that later in this video. For now, you want to take into account the type of carbon that is attached to the oxygen. That is, this is an sp3 carbon. Here, we have an sp2 carbon. So therefore, the CO stretch is going to be different. It's going to be higher. It's going to be between 1200 to 1300. And the reason for that is the resonance that can form here. So let's take this lone pair, let's form a pi bond, and let's break this pi bond. And now let's draw the resonance structure of the ester. And let's add the corresponding lone pairs. So we could see that the sp2 CO stretch of the ester has more double bond character than the sp3 CO stretch of the ether due to resonance. And why is that important? Well, as we've established, a double bond CO stretch has a higher wave number than a single bond CO stretch. So a CO stretch with more double bond character is going to have a higher wave number than the CO stretch with more single bond character.
When's the last time you seriously thought about your browser? Does it look like this? With Chrome, ads and...
Now we do have an sp3 carbon attached to the ester. So therefore, we're going to have this signal as well for the ester on the left. We're going to have two CO stretch, an sp2 CO stretch and an sp3 CO stretch. But the ether, it only has the sp3 CO stretch. And so that's how you could distinguish between an ester and an ether. The first characteristic is the carbonyl functional group. That alone is enough to distinguish it. But the second thing is the presence of the sp2 CO stretch versus the sp3 CO stretch. Now let's talk about primary and secondary amines before we go into amides. Now the primary amine, which has two hydrogen atoms attached to the nitrogen atom, it will show up as a double peak with a signal somewhere between 3300 and 3500. Now the secondary amine only has one hydrogen atom attached to the nitrogen atom. And so it's going to have a single peak between 3300 and 3500. So that's how you could distinguish the amine, the primary amine, from a secondary amine. Now the amide, it does have the carbonyl functional group. And so we're going to have a CO stretch very close to 1700. And we also have the NH2 group, so we're going to get this signal as well, between 3300 and 3500. So to distinguish an amide from an amine, you need to look for the presence of the carbonyl functional group. And to distinguish a primary amine from a secondary amine, look for the double peak in the primary amine and a single peak in a secondary amine. Now let's talk about alkanes, alkenes, and alkynes. The alkane CH stretch, it has a signal of around 2900, which we talked about earlier. The alkene C double bond C, that signal, it's a weak to medium signal which shows up around 1660. Now the C triple bond C of an alkyne functional group, that signal is also a weak signal and it shows up around 2100 to 20.
this will show you a sharp V, you know, and this will not be that very sharp if you see the difference, the peak difference. Got it?
And carbon single bond will be the sharpest?
Yes, carbon single bond will be the sharpest. No,
Okay.
carbon single bond will be this. Acha, carbon to carbon single bond.
Yeah, that's what I meant.
Then it will be that.
Okay.
200
Thank you.
wave numbers. Now the next thing we need to talk about is the CH stretch of an alkene and an alkyne. So the double bond CH stretch of an alkene, it shows up around 3000 to 3100. So relative to the alkane CH stretch, it's going to be slightly to the left of it. So here is the alkene CH stretch close to 3100. Now let's say if you have a terminal alkyne, and so you're going to have the alkyne CH stretch. This signal is even further to the left of around 3300. And so here is the alkane CH stretch, and then here would be the alkyne CH stretch. So this helps you to distinguish an internal alkyne from a terminal alkyne. And to distinguish an alkene from an alkyne, you could simply look at these two numbers. So let's talk about the effect of hybridization on a wave number. So here we have an sp3 CH stretch. This is an sp2 CH stretch. And here we have an sp CH stretch. So notice that as the S character increases, the wave number increases. The SP CH stretch, it composed of 50% S, 50% P. This is 25% S, 75% P. So as the S character increases, the wave number of the CH stretch goes up. Now, going back to alkanes, there's two other signals that you want to be familiar with. The first one is a CH3 bend, which has a signal of 1365 to 1385. And then the other one, it can vary between a CH bend, a CH2 bend, or a CH3 bend. And that can vary between 1400 and 1450. Now let's talk about the relationship between atomic mass and wave number. As the atomic mass goes up, the wave number goes down. So going from hydrogen all the way to bromine, we can see that the atomic mass is going up. But looking at the wave numbers, it decreases from 2900 centimeters to the minus 1 to an average of 550. And so there's an inverse relationship between atomic mass and the wave number at which a bond absorbs IR radiation. Now the next relationship that we need to consider is the one between bond strength and wave number. As the strength of a bond increases, the wave number goes up. We know that triple bonds are stronger than double bonds, and double bonds are stronger than single bonds. Thus, triple bonds will have a higher wave number than single bonds. We can see that in the case of alkynes relative to alkanes, in the case of nitriles versus amines, and carbonyls versus a C single bond O stretch. And it makes sense because more energy is required to stretch a triple bond compared to a single bond, because it's harder to pull 3 bonds than 1.
Time to scout.
And since wave number and energy are directly related, triple bonds will show up at a higher wave number in the IR spectrum. So that's another thing you want to take into account when dealing with IR spectroscopy. As the bond strength goes up, the wave number goes up. Now, another topic that we need to consider is conjugation. So here we have a ketone that is not part of a conjugated system, and it's going to absorb IR energy slightly higher than 1700. So this will be around 1720. Now for the conjugated ketone, it's going to absorb IR energy at a lower wave number. That is, in this case, around 1680. So make sure you understand that. Conjugated carbonyl groups, they will absorb IR energy at a lower wave number. Now the same is true for the double bond of an alkene. Here, this is a non-conjugated system, and so this alkene will absorb around 1650, 1660 in that area. Here we have a conjugated alkene, and so the absorption is going to be less. This one is going to be around 1600. So conjugated alkenes, they absorb IR energy at a lower wave number than regular alkenes. So remember, conjugation can reduce the wave number for ketones and alkenes. Now, it helps to remember something if you understand a reason why. Remember, we said that double bonds absorb energy at a higher wave number than single bonds. Let's look at the conjugated ketone. If we draw the resonance structure, we can put a single bond on that ketone. Let me color code this. And now we'll have a positive charge here. So looking at the double bond of the conjugated ketone, and let's compare it to the double bond of the regular ketone. Which one has more double bond character? The answer is this one. This one has more double bond character because it can't become a single bond through resonance. The conjugated ketone, it can become a single bond through resonance, so it has more single bond character. And now let's think about this. We said that double bonds have a higher wave number than single bonds. So because this ketone has more double bond character, it makes sense why it would have a higher wave number than the ketone with less double bond character. So as we've considered before, as the bond strength goes up, the wave number goes up. Double bonds have a higher wave number than single bonds. So that's basically it for this video. I wanted to give you a basic introduction into IR spectroscopy. Now I'm going to be posting another video that has a few practice problems where you can apply the information that you just learned. So when you're ready, you can just go to the YouTube search bar, type in IR spectroscopy, practice problems, and then just type in organic chemistry tutor.
Okay. Clear with IR?
Yeah, ma'am.
Okay, we'll go with mass spectroscopy and then we are done with the spectroscopy thing.
Yeah.
और बना लो फेक पेरेंट्स आनिया भी गई इज्जत भी गई
In this video, we're going to focus on mass spectroscopy. So here we have the mass spectrum of pentane. And just to give you a little background information on how this technology works. So basically, you would take a sample, like this one, pentane, and put it in a mass spectrometer. And what's going to happen is that sample is going to be vaporized, and then it's going to be ionized using an electron beam. Now, when it ionizes, it can fragment into radicals and cations, but only the positively charged ions will make it through the analyzer and reach the detector. And in this graph, on the y-axis, we have the relative abundance of the fragments. So this represents the quantity of the positively charged fragments that reach the detector. And on the x-axis, we have the mass to charge ratio. Now let's say if we get a methyl cation. Typically the charge will be +1. So if Z is 1, then M over Z becomes the mass of the fragment. So what we want to do in this example is we want to determine what fragments will form and which of these numbers these fragments correspond to. If you understand this, then you could use this to identify which molecule corresponds to which graph. But for now, let's identify the fragments that form in pentane if we put it in a mass spectrometer. So let's call this carbon 1, 2, 3, 4, 5. Now, if we break the C1-C2 bond, it can split up into a CH3 group and a butyl group. Now typically one is going to be a radical and the other one is going to have a positive charge.
CH3 into 2 groups.
Now carbon has an atomic weight of 12 and hydrogen is about 1. So CH3 is 15. CH2 has an atomic weight of 14. And if we add up 14 plus 14 plus 15 plus another 14, this will give us 57. So 57 could correspond to this particular fragment. Now we don't always have to get a methyl radical. We could get a methyl cation. If we do get a methyl cation, then this molecule will be a radical. So this is another possibility. But it's important to understand that only the positively charged fragments will reach the detector. And so the methyl cation could easily correspond to the peak that we see at 15.
Clear till here? Roger?
Yeah.
It depends on which one you consider the cation. If you take CH3 as the cation, then it will be corresponding to the 15 one. Relative abundance.
Do they break into chunks or something?
Yeah, they break it into 2 parts, cation and anionic part. You can say like this.
So it'll be either the first CH3 and the remaining, or the second CH3, CH2.
Yes, it can be done. Either this CH3 can be made as a cation and this as the anion, or the other way around. Got
Okay.
it? So this showed you both
Okay.
the ways. If this is made the cation, then you will get here the 15, the reading will be here. If we make this as the cation, then you will get the 57 depending on its molecular mass. Got it?
Yeah, okay.
Now what about the peak at 43? That peak is known as the base peak. It has a relative abundance of 100%. So everything is compared to the base peak. The peak at 72 is known as the parent peak, also called the M plus peak. And it turns out that it's simply the mass of the compound. If you add up 15, 14, 14, 14, and 15, this will give you the total molecular weight of pentane, which is about 72 grams per mole. And so that corresponds to the M plus peak. Now, if we break the C2-C3 bond, we can get these two fragments. We can get an ethyl radical or an ethyl cation, but I'm only going to focus on the cations at this point. Or we can get a propyl radical, or even a propyl cation.
See, when you need 72 at this point, what is this 72 at this point? Then this is the first two, CH2, CH3. This will give up to 72 here. Sorry, this will give up to 15. plus this is 15 plus this one is 14. So it will be 29. This peak will be for CH3, CH2 cation. And this peak with the maximum thing is this one. The part of this whole thing. The whole thing
Yeah.
represents this peak. Got it?
Yeah.
Now, anytime you see a CH2 group, it has a weight of 15, and the CH2 group has a weight of 14. So the ethyl cation has a weight of 29. So that corresponds to the peak that we see here. As for the propyl cation, if you add 14, 14, and 15, that will give you a total of 43. Or you could do 72 minus 29, and that'll give you 43. So the propyl cation corresponds to the base peak. Now here's a question for you. Why is the propyl cation the base peak and not the butyl cation?
This is how fast YouTube is with Brave. Notice how there's no pre-roll ads? And here's how you can see how
Cation. Let's compare both of them side by side. If we break the C1, C2 bond, we could get a methyl cation, and we could get a primary butyl cation. Now, which situation leads to the formation of more stable fragments? In the first scenario, where we break the C2, C3 bond, notice that we have a primary ethyl cation and a primary propyl cation. In the second situation, where we break the C1, C2 bond, we have a primary butyl cation and a methyl carbocation. So a methyl carbocation is less stable than a primary carbocation, which means it's easier to break the C2, C3 bond as opposed to the C1, C2 bond, because this will give us more stable fragments. And that's why this is more abundant, because it's easier to break the C2, C3 bond. Now, it's important to understand that both of these cations can rearrange to a more stable secondary carbocation. But the reason why this is the base peak is because it's easier to break the C2, C3 bond due to the formation of more stable carbocation fragments. This one is less stable, so it's going to be harder to form. And so that's why this corresponds to the base peak. Now let's clear away some of the stuff that we have on the board. So at this point, we've identified all the peaks. So the peak at 15 corresponds to the methyl cation. The peak at 29 corresponds to the ethyl cation. The peak at 43 corresponds to the propyl cation.
CH2,
And the peak at 57 corresponds to the butyl cation. At 72, it's the original compound that lost only one electron.
5 carbon group.
Now what about the peak at 41? How can we get that? So starting with the propyl cation, this molecule can lose 2 hydrogen radicals. And if it does so, what's going to happen is we're going to get an allylic carbocation.
Remove 2 hydrogen.
And this carbocation is stabilized by resonance. And so that's why
Single bond gets
it's
converted into
very
double
abundant as well, relative to the other fragments. So it's relatively easy to form this particular carbocation. It's primary and it's allylic. So if this has a mass to charge ratio of 43, and if we subtract 2 from that, then the mass of this particular fragment will be 41. You can add 14, CH is 13, plus another 14. That'll give you an M to Z ratio of 41. Now, it's also important to understand how the primary carbocation could rearrange into a secondary one. So let's start with the propylcation. A hydride shift can occur, converting the primary carbocation into a secondary one. So this is going to be CH and then CH3 with the plus charge on the secondary carbon. And so the M to Z ratio for this as well will be 43. So this carbocation can easily rearrange into this one as well.